Good day, everybody. And you're all very welcome to this session of the CNPS, which is one of our so-called alternative sessions, which are held every second week. There are more technical sessions where we go into a bit of detail. We give the speaker, something like an hour and a half uninterrupted time to make his presentation. And then we have a short question and answer session at the end and discussion. So we would ask you to avoid interrupting the speaker during the presentation, unless there's something really that you didn't understand and you need clarification on that. Well, then I don't think he minds that in an extreme situation. So today, actually, we're continuing once again with our detailed analysis of unipolar induction, and particularly the early experiments of Michael Faraday in electromagnetic induction. Now, we've had a number of sessions dealing with the subject, as you will know. We had actually three sessions given by Harry Ricker, looking at the original experiments of Faraday and all the various explanations, sometimes contradictory, that have ensued over the years. We've had a presentation by Bob Gray on applying Weber's electrodynamics to this problem, and we've had a session by myself on Kelly's repeat of Faraday's experiments and his inclusion of further experiments and explanation. So today we have James Keene, who actually has been attending our presentations. So I think it's given him a lot of ideas on applying the scientific method to this analysis. And today he's going to look at, what he's called problems in unipolar induction. And in particular, Faraday's experiments in this subject and their possible explanation. So we'll have time, as I say, at the end to enter into some Q&A and also some discussion, which will, give us some indication of how we might go further on this subject. So I'm handing it over to you, Jim. The floor is yours. So we can put Jim up there, Franklin. Let me see now.
Can I start now? Thank you, Ian. The typical components in unipolar induction experiments are shown here in one setup. There's been many different setups used, but in this particular presentation, I'll emphasize this sort of setup where we have a copper metal disc and it's spherically symmetrical around an axis and a magnet. And it's a bar magnet, which is cylindrical and again symmetrical around the axis. And one of the poles, north or south, is pointing toward and close to the disc. And the disc is separated from the magnet by a little bit of air. There may be, for example, brush contacts shown by this star here on the shaft to presumably measure the voltage between the center of the disc and the edge of the disc with a meter. And when the disc spins, typically a small voltage occurs. Now, by the way, my presentation will be less than an hour, I think. And so that we'll have plenty of time because our panel of experts here, I'm very interested to see what all of their comments and ideas are. Since, as Ian just mentioned, we've had a number of presentations, and I thank Harry Richter, Ian, and also Bob Gray for their presentations. And I did a little reading on the subject as a result of that and came up with some ideas which I'll present to you today. And I'm primarily, perhaps, might be considered more of an expert in particle physics and quantum mechanics. And so I have a ton of very thick books on electromagnetism, which I've studied over the years, but I don't consider myself an expert on electromagnetism per se within the whole sphere of the many topics covered by the discipline we call physics in these days. Now let's see, arrow, oh, good. So unipolar induction experiments. Does one pole of a magnet induce an electromagnetic field, which EMF, in a conductor, and if yes, under what conditions? Typical conditions or independent variables have been motion of the conductor, the magnet, or both. Measured induced voltages are quite low, mostly less than 50 millivolts, as I recall from the previous presentations here in these sessions. Experiments do not clearly exclude competing theories. Harry Richter did us a great service by reviewing this in great detail, theories by Maxwell, Faraday, Weber, and others regarding the induction effect mechanism. Apparently, experimentalists do not calculate or have not calculated expected measured millivolt predicted by a particular theory. This may have been mentioned in the previous sessions, but I just don't recall much talk about this. Thus, statistical analysis cannot be used to determine if measurements deviate significantly from expected values as a means to distinguish among competing theories. Now, our outline for today is 3 parts. First, I'll just present some background information, and probably most of the listeners here today are familiar with it, but I required a little review of some of these ideas, and perhaps it might be helpful, this background information. Second, possible problems with typical experimental designs in unipolar induction experiments. Third, how we might distinguish excuse me, between electrostatic generator and a unipolar induction effects. Okay, let's do this. Triboelectric effect, known centuries before Faraday's experiments in the 1830s and 1851, as Harry so well described to us. Tribo, the prefix tribo, comes from Greek for rubbing. The triboelectric effect, also known as triboelectric charging, is a type of contact electrification on which certain materials become electrically charged after they are separated from a different material with which they were in contact. Rubbing of two materials with each other increases the contact between their surfaces and hence the triboelectric effect. Rubbing glass with fur, for example, or a plastic comb through the hair can build up triboelectricity. Most everyday static electricity is triboelectric. The polarity and strength of the charges produced differ according to the materials, surface roughness, temperature, strain, and other properties. The mechanisms of triboelectrification or contact electrification, wow, that's a big word, have been debated for many years, with possible mechanisms including electron transfer from one material to the other, ion transfer, or the material species transfer between the two materials. While examples of the effect occur using two solid objects, here's an important point, ladies and gentlemen. The triboelectric effect can occur between a solid and a liquid or gas. For example, the copper discs or wires used in many experiments and surrounding air particles, respectively. The triboelectric effect with motion. Notice here in the upper right that sliding outward produces current in the opposite direction as sliding inward, shown here in the lower left. The current going one way here, going the other way here, depending upon the direction. Thus, a meter would show opposite voltage sign when motion direction is reversed. An effect also seen in so-called unipolar induction experiments, when the conductive disk rotation direction is reversed. Electrostatic generators. Let's review this in part one of our outline. The phenomena of static electricity requires a separation of positive and negative charges. I know most of you know all this, but this is my little review. I certainly needed a review of some of these ideas when I heard some of the presentations we've had recently. When two materials are in contact, electrons may move from one material to the other, which leaves an excess of positive charge in one material and an equal negative charge on the other. When the materials are separated, they retain this charge imbalance. Now, manual electrostatic generators, this is a whole class of gadgets and devices which various innovative researchers have developed in their garages, in their mother's garages, so to speak, over the years. They develop electrostatic charges and they work by using moving plates, drums, or belts to carry electric charge to a high potential electrode. In the Van de Graaff generator design, this is an important point here, I think, a special belt is used to transport charge to a conductor, which may accumulate net charge equivalent to a potential of thousands of volts with reference to another object such as earth ground. This special belt consists of a chain of alternating conductors and insulators, dielectric. Now, I'm going to be introducing the idea that the air between the magnet and the copper disc or conductor is actually could be like a Van de Graaff generator belt, consisting of a chain of alternating conductors, which would be air particles, and the space in which the air particles reside. In other words, the volume of the air, which is a dielectric insulator. The Van de Graaff generator is an electrostatic generator which uses a moving belt. Here's our moving belt. We go down, pick up some plus charges on this brush here, and as the belt moves around and on up, the plus charges can be removed by this brush and deposited on the disc, on the globe or sphere at the top. And this moving belt accumulates charge on a hollow metal globe, as I just mentioned, on the top of an insulated column, creating very high electric potentials. It produces very high voltage direct current electricity at low current levels, invented by American physicist Robert J. Van de Graaff in 1929. Okay, here's just a reminder, given that background, of our experimental setup. And typically there's 1 meter trying to measure the voltage between the shaft, which is presumably metal, so they'll have a brush on the shaft, which is the center of the disc, and the edge of the disc. Headline: unipolar induction experiments typically have all the components, or may have, I should say perhaps, all the component parts used in electrostatic generators. What's going on here? Do the tiny millivolt voltages generated in experiments which have been reported recently here represent function of a very poor electrostatic generator? Are the data consistent with a model, an electrostatic generator model? Questions. Now, hypothesize diverging radial EMF is what we have in the unipolar induction experiments, a radial diverging, if you see my mouse action here, from the center to the outside, causing the separation of charge between the center and the periphery of the disk. Now, that's what we hypothesize in the unipolar induction experiments, as I understand the presentations. Or do we have simple Coulomb repulsion of like charges? If we have an excess of charge in the disk, it could be that simply what's going on is Coulomb repulsion toward the periphery of the disk of like charges. Let's take a slice of that charged disk through the center. So here's our slice from right to left here, and let the position, let's designate the center of the disk as position R equals 0 through this one-dimensional analysis of the Coulomb repulsion question. And let's designate arbitrarily in arbitrary units the position of this charge on the right, Q2, equals R equals 1, its position, and the opposite position, R equals minus 1, for charge Q1, we'll just take two charges at each edge of the disk and their positions. Using this Coulomb equation here, we're going to then use Hot Basic, which, by the way, I'm the author of Hot Basic. It's a compiler, and it is a totally original compiler, taking the language you see here directly to machine language. There are no C libraries used, so that Hot Basic outclasses all C language compilers and virtually all other compilers, which Python or whatever you want to name, which are usually just based as front ends of usage of C libraries, C language libraries, which is rather inefficient compared to Hot Basic. So there's my little plug for Hot Basic. Anyway, that's why we have, that's why I'm using Hot Basic here, because I wrote the dang thing. Okay. In this simple little program, which took about 5 minutes to write, we can designate R1 and R2 as our two charge positions. And we can step through from the periphery at about 0.8 of the total distance to the edge from the center to minus 0.8 to plus 0.8, and for our position range. The DR1 and DR2 are simply the distance to the charges, and phi is our superimposition using the equation above, where Q is just set to 1 in the numerator here, of our two position distances R squared here, and that's our superimposition step, and we get phi, a potential, and we print it out, and we go to the next one, and here are our results. Notice that at the center of the disk, 0, we have an arbitrary value of 2. I say arbitrary because this is an unscaled abstract version of the charge separation problem. And at the periphery, or near the periphery of the disk, the voltage, or the field, as it were, the E field, is 25 compared to 2. That's a whole order, more than an order of a magnitude greater than the center. And at the other edge, also, we have the same difference with the center, of course. And so this seems to confirm that, yes, Coulomb repulsion could explain a voltage difference between the center of a charged disk and its periphery. Now, another possible area to look at in analyzing these experiments, this is part 2 here, possible triboelectric effects at the junctions with motion. the red boxes, okay? Now, of course, the brush to disk is a possible triboelectric effect because you only get the voltage recorded now in a millivolt meter here when the disk spins. So there would be motion at this junction. Also with the shaft. And I don't recall what the metal is or the material used in the shaft. I assume it's a conductive metal like iron, steel, or something like that for this brush here at this point. Now, there could also possibly be, I'm not saying that there are, triboelectric effects between the shaft and the fixed support for the shaft at one end of the shaft and the fixed support of the shaft at the other end where there would be motion when the disk is spinning. A third possible triboelectric effect area would be motion between the magnet mounted on the shaft and the shaft. However, I don't think this one is very relevant because if I understand everything that was presented here correctly, it doesn't matter if the magnet is rotated or not. So that, whether or not there's motion between the magnet and the shaft and a triboelectric effect between them wouldn't seem to be a possible factor at all, since that doesn't affect the experimental results. So that the brushes and the shaft to its fixed support interfaces could be a possible source of a triboelectric effect, a possible one. Oh, okay. Now the last area, the last red box here is the air to the disk interface. Now, what could be going on there? The electrostatic generator concept is charge accumulated when the disk spins. Okay. Now, the green arrows show that the unipolar magnetic field from the magnet may affect the air in the space between the magnet and the disk. And that air, which I'll give you a preview, which is polarized, would then have a triboelectric effect with the disk and possibly produce an effect, a voltage accumulation in the disk. Now, here's proton motion in a magnetic field. This is data from Binary Mechanics Lab, which is my site, as it were. Here we have proton motion from zero in an up-down y dimension with applying the north or south poles of a magnetic field to a simulation of space with protons in that space. And we see that the protons move in a direction in accordance in approximately the same amount of distance, 0, 2, 0, 2, minus 0, 2, 0.02. And depending upon which magnetic pole is applied. Now let's look at electrons. Whoa, we've got about the same thing. The electrons also move in the direction determined by the direction of the magnetic field. Notice the protons and electrons, although oppositely charged, move in the same direction given a particular polarity of the magnetic field applied. Now, the reference for this paper, or the link if you want to look at it in more detail, is shown at the top here. The proton displacement, as I indicated, was about 0.23 spots, which is, excuse me, a little congestion, which is about 0.23 spots. And the spot is a unit of structured space in binary mechanics. In about 10 binary mechanic lab simulator BMLS ticks, which are units of time. Electron displacement was about 0.35 spots in about 10 ticks. So the electron motion was about 50% greater than proton motion. So we have the result. Thus, a unipolar magnetic field would polarize air particles, which would be molecules of gas like nitrogen mostly, and then oxygen, or even particles of dust, whatever they are. Thus, a unipolar magnetic field would polarize those particles. Now, just a little side point off the main track of my presentation, you might say, is that for the proton, which is a hydrogen ion, of course, its motion was 3 femtometers in the illustration I just showed you. And that occurred in approximately 2.8 e to the minus 23rd seconds. This proton velocity was about almost 4% of the light speed. That is over 10,800 kilometers per second. Why do I mention this here in this presentation? I want to emphasize that the detailed data in BMLS output files enables precise calculations. For example, we might be able to even estimate the Teslas per a single L-type one-state bit. Now, I've used some terminology from binary mechanics, which you may not, and I'm aware that you may not be familiar with, but let's hang in there in terms of what is relevant to today's presentation. And of course, you can look up some of this terminology yourself if you wish at a later time. So what do we have here? Is charge accumulated when the disk spins? The green arrows indicate the possibility that the magnet polarizes air particles, which then have the second green arrow would be a possible triboelectric effect between these polarized air particles and the moving disk. Now, in an electrostatic generator, charge is accumulated. We might be able to distinguish that by using 2 meters, okay? Each one connected to earth ground. So we're measuring the shaft or the center of the disk to earth ground and the edge of the disk with the second meter to earth ground. In the in the unipolar magnetic induction work, where only 1 meter was used, we can't distinguish the fact that with the 2 meters, we might see that this meter would have show a millivolt reading opposite to the value shown by the other meter. Of course, the difference in the millivolts between the 2 meters should be approximately the millivolts we measured using 1 meter. This is just simple electric engineering, I suppose. Okay. Now, if charge is accumulated, however, in the disk, both meters would show millivolt changes of the same sign. In other words, increasing the amount of charge on the disk compared to earth ground. Now, what if we could get these effects without a magnet? My goodness, what could this be? Let's look at what if we had an electric field instead of a magnetic field. What happens to our protons and protons and electrons? Here we're applying a unidirectional electric field and looking in the vertical or direction, up or down, plus or minus, up or down, and we're looking at the proton Y displacement. Here the proton moves as it is predicted to move by electrostatic analysis and Coulomb's law and so forth. The positive proton is attracted to the negative field and repelled by a positive field. And the same occurs for electron motion. Now, while we saw that proton and electron motion in a magnetic field was in the same direction, the protons and electrons move in opposite directions in the electric field. Here's a similar page showing the results, and again, the reference to the paper if you want the details associated with it. The proton displacement was about 0.4 spots in about 35 BMLs ticks. The electron displacement was about 2.5 spots, again, a measure of distance in structured space in binary mechanics, in about the same amount of time, 35 ticks. So the electron motion was about 625% greater than proton motion. Thus, the electric field was very good in this particular example in polarizing air particles, or so we at least would expect. And then a similar calculation, if you'll bear with me, for the proton motion in this setup, we had the distance was 5.4 femtometers, and this was approximately 1 to the e minus 22 seconds, or with giving us a proton velocity of almost 1.8% of the speed of light. That's over 5,000 kilometers per second. Now, whenever I look at this particular slide and its companion slide in the magnetic field with the velocity shown there, 10,000 kilometers per second, I think of those videos that they showed recently of some sort of craft that U.S. fighter pilots found over the ocean, and they would suddenly scoot off at seemingly velocities beyond what physics could account for. And that's the kind of velocities, even like 60 kilometers, like 1/100th of this. Even 60 kilometers per second, I would think in the blink of an eye, it would almost appear like an object just disappeared and just completely went away so fast that it appears to have disappeared. Anyway, getting back to our line here, I want to emphasize again the importance of precise calculations. Detailed data in the output files of the Binary Mechanics Lab simulator enables precise calculations. For example, is the data consistent with Coulomb's law? And if so, have we derived this law without use of any so-called fundamental constants? So that there's a lot of opportunity there, if you will. So our E field instead of unipolar magnetic field. Let's have our same disk, but instead of having a unipolar magnetic field, we're going to have an electrostatic field, as if the disk was between the plates of between the plates of a capacitor, two parallel conductive plates here hooked up to some DC power supply to give us an E field in affecting the disk in between. Now, notice we could make holes in these two plates to run our shaft through the holes, which would not be touching, the shaft would not be touching the disc of our capacitor, as it were, charge capacitor, so that we could, with such an axis, spin the disc. Now, when we rotate the disc in an E field, do we get the same effect as a magnet with no magnet? We predict an EMF in the disc proportional to the E field level. Okay. Now, a Keene summary, pun intended. The unipolar induction hypothesis would predict an outward radially divergent EMF. Thus, the shaft ground meter should show a voltage of reverse sign compared to the disc edge ground meter. If both meters show voltages of the same sign, or if the E-field experiment works that I just presented with no magnet, the electrostatic generator hypothesis might be favored. In all cases, the measured voltages are predicted to be proportional to temperature and pressure. Now, the purpose of my presentation today is perhaps to have some of our panel of experts here put on their thinking caps. And I'm not saying that unipolar induction experiments are wrong. My position is that perhaps there's some things we want to look at to exclude alternative explanations of the very small voltages which are typically observed. And with that, I'll hand it back to Ian to manage any possible discussion or questions, should there be any. I hope this has been stimulating, and I thank you for listening and your patience in so listening. And I thank again the previous presenters which have stimulated my thought in this presentation. Those presenters were so good that they forced me, as it were, to put on my thinking cap and to say, what is really going on here? And hopefully I've raised some questions which are of some interest. Okay, Ian, it's all for you, sir. Tell me when I should unshare my screen so I can see what you all are doing.
Yeah, you could possibly unshare your screen if you wish now.
Okay, how do I do that? Let's see.
You might have been going to present.
And show, and then what? Okay, I ended the show.
Unshow. You might have to click that again, Jim.
Yeah, it's fine.
Screen.
There, control the.
There we go.
Okay, it's worked.
I stopped the screen.
Okay, it's worked. Well, first of all, I'd like to thank Jim very much for the considerable work that he's put into this brief presentation, because he first mooted this triboelectric hypothesis during the previous sessions that we gave on the subject, and he's obviously gone to a lot of trouble now to detail that and to further his ideas, and actually, very importantly, propose maybe 2 or 3 experiments which might be done to rule in or rule out this hypothesis as being central to the question of the unipolar induction experiments. Now, there are some questions which you might like to put up on the chat board, and we can try to answer those if necessary, or get Jim to address them. There is also in the green room possibilities of coming in, and I think that's what when Jim very kindly talked about a panel of experts. I don't know, we might have specialized in this subject at some stage, but I don't know if we're really experts. We can come in and talk about that. So before inviting others to come in, I'd just like to ask something maybe, because as is indicated, Jim, when the first experiments were basically done, starting with Faraday's experiments, there were a couple of results which were described as paradoxes. So let's take the 2 ostensible paradoxes with the unipolar experiment: the magnet, the disk, as you showed, and the circuit, the meter. Now, so the first, number 1, I'll give 2. Number 1 is when the magnet moves, you get no induced EMF. So that seemed to go counter to all preconceived ideas. And then number 2 is when the magnet and the disk move in unison, you get an EMF. Again, that seemed to go counter to all ideas of induction owing to relative motion. So those 2 paradoxes, how could they be explained at all on the basis of the triboelectric electrostatic induction?
Okay, the first paradox was when the magnets, as was, I believe, discussed in some detail by in the Harry Richter sessions, and I touched on it here, thanks to Harry, of course, the the magnet is symmetrical, and perhaps the magnetic field lines are not really changing when the magnet is spinning. So therefore, it doesn't matter whether the magnet spins. And the second paradox, did I cover both paradoxes there, or just one?
Maybe just one, the first one. The second one was where there's no relative motion between the disk and the magnet, and yet you get an EMF.
There's no relative motion.
So in other words,
yeah. Well, in other words, both are spinning.
Quite so, yes.
And they're both spinning on, attached to the same axis, and therefore the velocities involved would be comparable, and so forth and so on. Okay, thank you for that clarification, Ian. Well, when they're both spinning, if the EMF lines, as it were, we're calling them lines, I guess, are not really moving in any substantial or measurable way, we wouldn't see the difference between the disk spinning without the magnet spinning and the disk spinning with the magnet spinning. And I think Harry Richter very well presented this. And I don't really consider that to be a paradox at all. It's just
indeed, Jim, if the disk is moving, whether the magnet moves or not is not relevant. That is true, because if the disk is moving and the magnet is stationary, well, you get an EMF, and if the magnet moves with the disk, you get an EMF. But that's not the second paradox. The second paradox is that if the disk is moving, if you like, you get an EMF. But if the magnet is moving with the disk, you don't get an EMF.
If the magnet with the disk, you don't get an EMF.
Sorry, I beg your pardon. You do get an EMF. Sorry, I'm getting confused now. If the magnet is moving with the disk, you get an EMF. And if the magnet is not moving, but the disk is moving, you get an EMF.
Right. Well, that would indicate that whether or not the magnet is moving is not does not explain the effect one way or the other. The magnet can be stationary or moving. As long as the disk is moving, you have an effect. This is classical experimental physics. You can exclude an independent variable, magnet moving or not, by measuring your dependent variable, the voltage on the disk, in two conditions, magnet moving or not, and exclude, this is just classical experimental physics. Perhaps I don't understand what the real basis
I suppose what I'm saying is one can try to enumerate explanations of this. And you just gave an explanation of the first paradox, and others have given other ones. I mean, the initial idea that the field lines didn't move with the magnet, things like that. You can start bringing out a lot of hypotheses. Well, I introduced the major hypothesis with regard to the effect on the secondary circuit. That was another explanation. But I suppose what I'm asking now is these so-called, whatever you want to call them, paradoxes or something that's needed to be explained, can that be explained simply on the basis of electrostatic generation, as distinct from all the panoply of explanations that we've all indulged in based on the electromagnetic induction hypothesis? I mean, maybe the answer is no, Jim, because, in order to substantiate whether this is central to the explanation of the creation of the EMF, one would have to engage in those experiments which you have explained. For example, getting the opposite voltage, with 2 meters and so on. But
right. That was the purpose of my presentation, to present ideas which may, okay, with bright minds, no matter what you do in physics these days, in your garage, as it were, somebody's going to find a problem with it. But I've tried to present two types of experiments: the dual meter experiment compared to the single meter, and the electrostatic field, the E field experiment without a magnet at all, to which may help clarify these issues. That's what my goal has been, to try to clarify the issues, not to necessarily present a dogmatic conclusion one way or the other. Now,
okay. Well, that's
now
fair enough.
this may be relevant or not, or it may just be complete idiocy. But I set up on the table here my meter, high input impedance meter, and I just connected the two lines to each other to form a loop, and passed a fairly strong magnet around the wires, and was moving this whole relative motion of one or the other, the wire or the magnet, and I couldn't get any voltages. This probably means little or next to nothing, since perhaps my meter was not good enough to detect the voltages and so on. But I just couldn't see any induced EMF by moving a magnet from a speaker, disassembled speaker, around the wire. But that could just be irrelevant in terms of today's session. But I will admit that I like to tinker, and I did get my meter and a magnet out and play with it, but I couldn't see anything, which I could then call unipolar induction.
Okay, well, I suppose the basis of my raising this in the first place, and we can discuss this a lot more later, was to indicate that, with respect, I mean, you've given a hypothesis, and that's fine. It's as good or as bad as any other hypothesis. There's no reason for believing in it. There's no reason for not believing in it. But you've given an indication of a couple of experiments, 2 or 3 experiments that could be done to clinch this. And that would be well worth doing. But I was trying to see that if you had any sort of a priori explanation of things which had puzzled people working on the basis of the electromagnetic induction experiments, and if you had sort of something which gelled in the mind, crystal clear, you said, right, that seems to be quite clear. Well, then it would give a sort of an a priori preference to the triboelectric hypothesis. But at the moment, it seems to be, well, let's be kind. It's on a level playing field. There's no reason to believe it. There's no reason not to believe it. And one would have to perform the experiments you've enumerated. Is that fair enough, Jim?
I think that's a good summary. Yes, sir.
Okay. Now, let's see. Toby has put up a thing which Franklin has looked at. Does the strength of the magnetic Gauss increase the voltage output? If yes, how does that relate to the hypothesis presented? Well, if I may just come in very, very briefly, I've already said to Toby that Kelly's experiments showed that when the strength of the field in Gauss it increased because you were closer to the magnet, it did give an increased EMF. But he's asking what is the possible relationship to the triboelectric hypothesis?
Oh, okay. Well, I from work at Binary Mechanics Lab, which I presented, the increased magnetic field would presumably polarize the air particles more, thus creating more opportunity for a polarized particle in quote unquote contact with the moving disk to participate in a triboelectric effect which would lead to accumulations of charge. So yes, Toby, an increased magnetic field would increase the measured voltage, in my thinking, as you have expressed.
Okay, so that's consistent with maybe some other experiments that have been done, Jim's explanation of that.
In other words, the correlation between the strength of the magnetic field and the voltages measured in previous experiments is consistent with both the triboelectric effect hypothesis between the disk and air and the unipolar induction hypothesis. In other words, it doesn't distinguish between the two.
Yeah, yes, quite so. It's another a point where we cannot distinguish between the two, and therefore the experiments would have to be done to discriminate between them.
Yes, sir.
Okay.
That seems to be my conclusion there.
Yeah, your modest conclusion. You're not putting this upon us as dogma. Franklin was asking what is meant by polarized. An electron is simply attracted to a positive field and repelled by a negative one, I think he means there. It is not polarized.
Okay. That's a good question, Franklin. What is polarized? What is the polarized atom, for example? If let's take an arbitrary single dimension situation for, let's say, a water molecule. Let's say the two hydrogens are to the left on our horizontal X scale, and we would say that it is polarized in the X dimension because there's more positive charge to the left on this X scale than to the right. With a single hydrogen atom, and we don't have those here in these experiments because I assume the air doesn't have much hydrogen gas in it, but it would simply be, again, to talk about the same thing in terms of the significance of this polarization at the atomic level, that the electron spends more time to one side, to the left or to the right, compared to the proton, which is positively charged. And that's what we talk about. That's what we mean by polarized air particles. So let's say our disk is to the left on this slice of the disk that I showed in one of the slides. If the air is polarized in one direction or the other, depending upon north or south poles, which is another independent variable, by switching the polarity of the magnet in these unipolar induction experiments, you reverse the EMF, the supposed EMF induced in the disk, right? Well, that would also the north and south pole reversal with the triboelectric effect that I talked about would also reverse the polarity of the air particles in contact with the disk, thereby favoring a positive or a negative net charge accumulation in the disk. So again, the two effects are indistinguishable when we manipulate the independent variable of magnet polarity, north or south, close to the disk. Did that answer the question, Franklin, about polarizing air particles?
Yeah, so that's an interesting point that you can kind of get the same effect. Although I'm just actually not familiar with the concept that a magnetic field can polarize gas molecules, for example. I would actually be very surprised about that because generally a hydrogen atom with a positive and negative, I would think, naively that the magnetic field should really have no effect on that. My other question was that you showed the graph and you showed the electron and proton movement, but it would move initially very fast. And then the graph just shows it flattening out. So I'm not sure exactly what you're showing there. I would expect that if there's any motion, it would just keep on going. But it flattened out.
Good point. Good point. Oh, okay. A perhaps limitation in the way the simulator is able to operate. I'm taking your second point first here, Franklin, and thank you for raising that point. It's an important point. All I could do was set the magnetic or the electric fields in the two sets of illustrations I showed of the motion of the proton and electron particles in the initial state. So as those fields, of course, are not replenished during the 10 or 35 ticks shown in the graphs, so that they decay. So that basically we're saying with an injection of a magnetic pulse at the very beginning, we could put this in words in this way. We're injecting a magnetic pulse or an electrostatic field pulse at the very beginning of the simulation. This will decay. Why would each decay? Well, in the case of the electrostatic field pulse, like charges would repel each other, which would decay the concentration of the like charges at the top or the bottom of the simulated space, and therefore the particles don't, as you say, just continue going off into continue moving. If we reprogram the simulator so that we could keep adding or replenishing the magnetic or electrostatic fields applied at the very initial state of the simulation, we would then be able to show continuing motion. With regard to the polarization of particles, I have made what I consider to be a no-brainer step of logic. If the electrons move further than the protons, as shown, in either the magnetic or the electric field applied initially at the beginning of the simulation. In the case of hydrogen atoms, the electrons would then be, those atoms would be polarized. And I'm not sure if this is actually, as Franklin pointed out, he said he'd never heard of a magnetic field polarizing single atoms, spatially polarizing them in terms of the orientation of a net positive or negative charge. Well, it could be that my paper should be read by a great many people, showing that effect, that it in fact occurs.
Yeah, that would have you could experiment. That's something you could experimentally actually verify or deny. Because as in physics, we that's how we do things. We make equations and do calculations, but ultimately, you'd have to show that effect. I mean, I would be interested, if I had hydrogen atoms, they can do things like magnetic resonances. They can actually tell which direction things are pointed. I mean, I'm just thinking about it. Magnetic imaging actually uses very strong magnetic fields to polarize, I think, the hydrogen in your body. And then when they release the field, that's how they actually image what's in you, because of the way that it depolarizes, I think. So
very interesting.
That might be some, I'm not sure if it's 100% related, but that does come up in the question of how do you detect whether something has actually been polarized that way. And they do use magnetic field apparently to.
Well, let me ask you, Franklin, and all of our experts, as a question to toss around, since this appears to be a new result in the binary mechanics lab data that I presented. Would this be expected by the Maxwell equations? The fact that the electrons move further than the protons. I could say, for example, in the magnetic field that the mass of the electrons are less than the mass of the protons, and applying the same magnetic force, quote unquote, you might expect that the electrons then would move further. In my little simulation there, which by the way was a pilot study, I showed one trial. It's amazing how consistent the results were with one trial only. Imagine if many trials were run and those curves were average. We'd have a nice, beautiful curve showing the movement and the velocity and the acceleration, and then the stable effect once the field dissipates. Yes, I mean, this is an interesting area.
Right. Well, if I may just make a suggestion, we're putting it to you, which is fine, and you're manfully dealing with these subjects. I've made some points, and Franklin has. I see Harry Ricker is here, and I'm wondering if his audio is working. Could I bring him up to pose a few teasers to you, Jim? Harry,
Sure.
okay, let me try to
Well,
do that.
remember, I'm not the expert here, okay?
Yeah, no,
I'm
but
just
you presented an hypothesis, which I suppose we're trying to see whether there's anything in it or whether it's just neutral. And Harry has looked into this subject as I have, and we, Franklin has as well. So I'd like to hear what Harry has. He might have some pressing points for you to consider. Harry, have you any
Okay,
response
it's
to James?
working. I'm kind of surprised it's working.
It's working perfectly.
Considered the past.
Just when we don't need you, when you're not speaking,
yeah,
it works.
I'm puzzled by that. I'm going to say I really found this kind of interesting because I think this is another subject that's worthy of being investigated, but I don't think that it really explains unipolar induction. I think the issue is there's a big enough mystery surrounding triboelectricity and what's involved there that deserves an investigation in itself, because I don't really believe the standard books and all what they have to say. I don't understand, frankly, to be honest with you, I don't understand how rubbing two dielectrics together creates electricity. They claim that there's an exchange of electrons produced by rubbing insulators. So in other words, materials which don't conduct electricity when they're rubbed together. That doesn't make any sense to me. Jim's presentation kind of puts a different light on that subject, which I think is a difficult problem. There's also the other area of applicability would be why does lightning occur in thunderstorms? I don't think any of the scientific books or any of the people have very good explanation for how lightning is produced in thunderstorms. And to me, that looks like it's a triboelectric effect. If what Jim is saying makes sense, then that could be applied to that problem, which in my mind is an unsolved problem.
Points well taken, Harry, and thanks for your presentations, which inspired me to look into this a bit. I found it very, very interesting.
Okay, now about your theory and its applicability to unipolar induction. There have been many attempts to measure electric charge buildup on the disk when it's spinning, and they've all been negative. So I'm not sure how that relates to your theory. I think your theory, as I understand what you're saying, is that there would be a charge produced on the disk when it's spinning. And my understanding of the experiments is that no such electric field effect is observed in any of the experiments. So that's kind of my comment on that.
Well, I'd like to see, with all due respect here, Harry, what the experimental setups were in those experiments which have excluded charge buildup. In the particular paradigm which I presented, which was based off of the video which Ian showed in his presentation with the spinning disc on the shaft, I just took that. You presented many different setups. 2 meters,
Well,
in my opinion.
Let me answer your question.
Good. Thank you. Please.
Cramp and Norgrove originally did this, where they took a spinning magnet and tried to measure the electrostatic field that would be produced. Now, you would say that probably was not exactly. I'm not really, my memory is not clear, but there's Cramp in Norgrove. That's a famous paper. I think they were the first, and I can't.
You're breaking just a little there.
But really were experiments that were in October. Am I having a problem seeing things coming on and off?
Yeah, it's gone a bit.
Is everything working?
It's working now, but it was interrupted there a moment. We missed a little.
All right. In the I'm getting old here, and I can't remember the names. When I originally gave this presentation, I was talking about the experiments that were done that were published in October of last year, and I forget the names of those people. I think they published the paper. Their claim was Faraday paradox resolved, or resolution of the Faraday paradox. That was the first presentation that I gave on this subject. And what the technique was that they mounted a integrated circuit onto the spinning disk to measure the voltage across the spinning disk. And they didn't measure any voltage. Okay. And that was also done by, in the Unipolar Induction handbook, or Unipolar handbook. And I can't remember his name. Barney. I wish I could remember his name. My memory is so bad. He did a similar experiment where he made a little voltage comparator IC circuit with a light bulb, and essentially attach that to the spinning disk. And the theory is that the light bulb would light up if there were voltage measured on the disk. In other words, if there was a potential across the disk would be the best terminology, I think. That he didn't detect anything.
Well, that would be also explainable by Coulomb repulsion, as I presented.
I'm just telling you what the experiments have been done. Okay, I'm not really sure exactly. As I understand it, I think you're saying that there should be a voltage, because you're showing in your picture, you showed plus charges on the rim of the disk. And so my assumption is there should be an electric field across the disk. Okay. And my point is, no experiments have shown the existence of such an electric field.
Well, that seems to rule out unipolar induction completely. If no experiments have shown such a radially divergent EMF on the spinning disk, we simply unipolar induction has been ruled out.
Well, okay. I think I've commented on this before. This is another of the paradoxes in my mind. I guess this really boils down to what the paradox is. There's no, the theories that I talked about, the 4 theories, and then the experiments that were done that were published in October. They verified that all 4 theories could, and now you've introduced a 5th theory. So now 5 theories that are consistent with the experimental results. That's not really good for science. I mean, that doesn't answer any of our questions. And that's, to me, the whole problem with unipolar induction is that it is resistant to the scientific method. Science has not been able to solve this problem. And what does that mean about scientific method and how's it being conducted? That's been my big issue that I've been asking. Why is this happening?
Agreed 100% here, Harry.
Who said that? Did you say that, Jim?
Yeah, I said that I agreed 100% with what Harry just said. And in one of my first slides, in the background section, I believe it was, that noted that I didn't recall, I'm being very cautious in how I state this, I didn't recall in Harry's excellent presentations actual calculations being done to allow distinguishing between one and the other theories. If Maxwell's equations are so great, why can't you calculate what the measured voltage would be? And it might be different than what Weber's idea would calculate, and so forth. And then you could use statistics to say, well, our recorded millivolts is closer to Maxwell's theory than it is to XYZ other theory. Yes, Harry, please go on, sir.
Okay, I wanted to comment on this and say that I believe that the theories, the way they're set up, they all give the same result as far as the voltage that would be predicted. Where they differ is where is the physical mechanism that is producing the voltage. That's the difference, has to do with the physical mechanism, not the predicted results.
That's an important clarification. Thank you.
Didn't you mention?
That's kind of why this.
Sorry, Harry.
I was going to say that's kind of why. I'm sorry.
Yeah, sorry. Sorry, just to point out, but if I may, do you remember the experiment? Well, Jim referred to it. I showed it on my video. It was done by a gentleman by the name of Cumming. And I think it was you, Harry, who pointed out that they were using like a sort of a drill to tag the disk, and that would have been earthed, I think you said. So I suppose this is a bit of a question to Jim, if you follow what I'm saying. I think it was Harry who first raised in regard to that short video of 7 minutes that I showed with the experiment, that the drill, the shaft, which was attached to the center of the drill, would have been earthed. It would have been connected to the ground, and that would perhaps have obviated any triboelectric effects.
Well, they would need. Wouldn't they need 2 meters in that case? They would need 2 meters in that case. 2 meters.
Well, they just gave one. Yeah.
Well, then
what I said was that the drill. Okay, I think in that case we could. I'm just supposing that the drill would have to be grounded because it's a electromechanical device, and I think the electrical standards require that there be a grounded connection.
Yeah, well, we don't know that. I mean, that seems logical, all right, but he didn't give those details in the experiment.
Right.
Yeah. Right. Well, even if the shaft is grounded, even if the shaft is grounded, it doesn't.
Here we go.
Rule out an error.
The system doesn't like it.
You're both speaking at the moment. I think there's a bit of a delay in the line.
I'm not going to disagree with that. Yeah, the delay is because we got people from different continents, and
right.
It's having trouble here when Ian speaks and I speak. Okay, what was I going to say? All right. I think your presentation is really interesting in that I don't really believe this business of the Triboelectric, and this is a famous thing, and I think it's the first experiments in electricity were done with triboelectricity. Francis Hawksby, and the Royal experimenter for the Royal Society, and then the famous work that was done early on in electricity. And my point is, I don't think that's really very satisfactorily well explained by the current theories. So I think James has given us a lot of food to think about with respect to that particular issue. as far as unipolar induction is concerned, it's a low voltage effect, and triboelectric effects seem to be high voltage effects. And so I'm not really sure that it's a triboelectric effect. Now, the other side is that Mueller in his experiments, Francisco Mueller in his experiments, did his experiments differently, because he says in his papers that he had so many issues with noise created by the friction and the triboelectric effects involved, that he designed his experiments to eliminate that as a factor in his experiments. So he took that into consideration when he did his work. So that would be my comment there. I think he did, he was.
You just cut off there again.
Well, where of that issue.
Can I comment, Ian?
Yeah, please do, Jim.
In what I recall of the video, it was a battery-powered drill that was used, and there was no ground. But and one person put up there on the caption on the lower part of the screen a few minutes ago that most drills that are powered by, not by battery, but by electric AC current, don't have a ground pin in the cord. And so there wouldn't be necessarily a ground in the system. But I would go so far as to say that with only 1 meter, even if the shaft were grounded, okay, you cannot exclude the air to disc motion triboelectric effect that I postulated as a possibility. I'm not saying that it's definite, but it's a possibility. You need the 2 meters. If there's an EMF developed in the disc, the 1 meter should show an opposite voltage with reference to ground compared to the meter to the disc periphery. And therefore, you need 2 meters in order to distinguish between an electrostatic generator and the unipolar induction. A further point is that there is no voltage limit from 0 on up to thousands of volts in the triboelectric effects involved in, say, a Van der Graaf type generator. So that if we shouldn't say that simply because the millivolts are small, that triboelectric effect between air and the disc moving is ruled out. It could just be that it's a very poor, and I would expect it to be a very poor electrostatic generator. And so I'm not surprised that the volts are very, very small.
Again, your theory makes more sense in explaining the electricity generated in a thunderstorm and the high voltages and triboelectric generators than in the case of the unipolar generator.
Well, in fact,
I don't know what else I can say.
I received an email from somebody that I won't mention the name because I don't have permission, but if that person is here now, they can chime in, that they were, due to my work, and by the way, I made a video of this on the BitChute, so on this presentation today, unipolar induction problems with it. And this person is interested in the generation of the high potential up there in the atmosphere that's responsible for lightning discharges. And and the possible role of a triboelectric effect with, wind moving air that may be polarized, et cetera, et cetera. And if that person is here, I won't name him because I consider emails to be private. I'm not going to publicly speak for somebody else by name, but if that person is here, they may want to chime in.
Okay,
I personally think that that this is an area which needs to be discussed further, and perhaps
it's an
we can talk
undecided
about it in
matter.
some future.
But there's a question. There's a question here that's been put up under the John Chappell label, but I think it was first posed by Denny. And I'm just wondering if Dennis Allen is there, if he'd like to come in and just explain what he's questioning Babbage. Are you there, Denny?
Yes.
Good.
Can you hear me?
Yeah, just about. You're low. Your volume is low.
Okay, I'll turn it up.
Yeah, that's better.
Okay, well, first, I have 2 points. First of all, Harry pointed out that Faraday was worried about explaining the Babbage-Aragno, I think it was, experiment, where you have a magnet underneath the disk and you rotate the magnet and the disk starts to rotate too, although there's no connection. How would that be explained by this electrostatic effect that James is talking about?
So this is possibly a bit like the Arago disk.
Yeah, that's what I'm talking about.
Yes.
So
well, here we're
not connected with that too.
In response to Dennis.
Yeah.
In response to Dennis, hello, Danny. That would seem to be an entirely different experiment, and because you're talking about moving a magnet, inducing motion in another object, and then I would ask, well, what was the disk made of? Was it copper? Was it iron, or what was the disk made of? And so here we're talking about motion of a magnetic field moving another object. Iron is attracted to a magnet. I mean, that's a whole other analysis. We're not talking about electricity here anymore, explicitly at least.
Well, the idea is that a current is induced by the rotation of the magnet, and that rubs against the ion lattice and causes motion to be induced. Whereas if you take your triboelectric effect, I don't, if it's really, or your electrostatic experiment where you have two plates and the thing is distance between them and turning, I don't see how. It seems like the old explanation of Maxwell's equations say there's a lot more, explains this a lot better than your effect, your triboelectric effect.
That may be true, yes.
And the other point I wanted to bring up was thunderstorms. In the book by the Granows, Peter and Neil Granow, the one on, let's see, I've got it right here, I think. Yes. Can you see that? They explain
non-Newtonian.
They explain thunderstorms and the thunder and the lightning and so on in terms of Ampere's experiments and instantaneous action at a distance. And they so if you're interested in explaining that, Harry, you might look at this book. I'll hold it up again. Maybe it's Newtonian Electrodynamics by Peter and Neil Granow. And it's a 1995 book, and it's hard to get, and it's expensive, but it's very enlightening, I think. And that'll be it.
Did you say, Denny, that they explain it in terms of action at a distance?
Yes, their whole idea is action at a distance. They reject field theory.
Oh, okay.
And that's why they explain there's a multiplicative factor of 2,000, as I mentioned in a previous. Whereas if you have the Ampere hairpin thing and you turn it into an electrostatic pendulum, then the Maxwell equation explanation using the the Lorentz law of force is off by a multiplicative factor of 2,000 over 2,000, as opposed to the electric effect that they introduced in this book, the two Granoffs introduced in this book I just showed you.
Right, the plot thickens. but you know, am I being a bit too bold if I suggest, Jim, that you are really not more convinced that this is the central explanation than we are? I mean, you're merely pointing out to us that this is a phenomenon which is worth investigating. There are certain reasons why we think it could possibly have an effect, but the jury is still out because we haven't performed these experiments. So we don't know one way or the other. I mean, you're not advocating that this is definitely the explanation.
No, that's correct, Ian. Now, in terms of what Dennis was just saying, one could use the kind of experimental setup that I showed based upon the video that Ian showed in his presentation, you know, of the disc on the shaft and so forth. And hey, you could let the disc be unattached to the shaft and spin the magnet and see if that starts to spin the disc. Right?
Well,
I mean, excuse me?
That was the experiment, this Babbage-Aragno experiment, where the magnet spun and then the disc started to spin in the same direction.
Okay, well, that's very interesting.
Yeah, I thought so too.
And was one of the reasons why they undertook this in the first place to establish whether the field actually moved with the magnet or not?
Yes.
Right. Okay. Right. Okay, a couple of other things which Franklin is looking at. I've been looking at is the Stern-Gerlach experiment shows that a differential magnetic field will cause a neutral atom silver to have two possible deflections. Yeah, I mean, this was ostensibly meant to show the quantum effects, I suppose, discrete quantum effects.
Well, it shows, it could also be taken to show, could it not, that the magnetic field is polarizing the silver atoms, as I suggested, as a possibility.
Okay. Now, what would happen if we ran the experiment in a vacuum? Yeah, what would you say to that, Jim?
You shouldn't see the voltages if they were due to a triboelectric effect with the air particles.
That's another experiment which we could do. I mean, I lament that we don't have Kelly around, because he'd be still fiddling around with his apparatus, and he could perform these experiments very easily for us and determine.
Well, with all due respect, in my last slide, I covered all of these experiments. I said that the effects would be proportional to temperature and pressure. Vacuum is simply a low pressure. And so, you know, like I already covered and predicted what the results would be if the electrostatic generator model were the best model for the results obtained.
Yes, but we'd have to determine whether those results were indeed found, or the contrary. If the contrary were found, well, then that would rule out the electrostatic effect. So we still don't know about that. You know, you've merely predicted what would happen if this hypothesis were correct.
Correct. Yeah. I mean, and this is what we have. Let me just give an anecdote from biomedicine, if I may. For years and years, people were getting very different results with regard to calcium ion transport in and out of cells. And two different labs were at each other's throat trying to replicate each other's experiments. And it turned out that the discrepancy was how many times one of the labs washed their glassware. In other words, calcium ions were binding to the glass in their test tubes. And the results they obtained in these experiments was due to a little methodological difference, such as the number of times one of the labs washed their glassware, to make it perfectly clean of debris, compared to the other lab. So this is, so these fine methodological problems can be sorted out with time. And as I said in my last slide, pressure and temperature. You could just heat the whole apparatus or cool it and measure the amounts of millivolts using the 2 meters, I might say. And that I would predict that temperature and pressure, either increasing pressure or decreasing it, i.e. running the experiment in a vacuum or a partial vacuum, as we might say, would have an effect. So I've already set forth those tests that could be done.
I see, by the way, that we have another gentleman in the green room now, Eric Reiter here. So, Eric, if I brought you up, would you like to pose some point for discussion or question to Jim here?
Okay.
Okay. Go ahead. You're welcome.
I'm here, but I was just intending to be passive. I haven't done these experiments, but it still seemed very straightforward to me that the Lorentz force would explain the whole thing. And there was some objection when I brought it up before that there was something wrong with it. I never heard what was wrong with the Lorentz force to explain the induced voltage of the spinning disk. So, I mentioned it a few times, like, well, what's wrong with it on Facebook and YouTube? The Lorentz force is used all over the place. With you see it in the old style television sets. So, there was some kind of objection from Harry Ricker that some kind of relativistic effect. I don't know what it was. I just like to see, well, why is the Lorentz force thrown out? So I'd like to just start there. Then, well, I could say a few more things. This business about whether the apparatus is grounded or not, I don't think makes any difference at all. I mean, you want to have 2 meters. When you measure potential, you just have a meter that measures the potential from 2 places. I mean, let me just try to see if I could draw a disk and a magnet. And, well, here's the experiment. Here's north, south. And you got a better light.
It's a bit hard to see that.
Right, yeah, right. I know.
Now that's better, a little better. We can see.
Yeah. So, well, what is it? You're going to measure the potential here. There'll be some. What happened?
I don't know what happened there. Yeah.
All right. So I'm just holding my camera. My phone.
At a distance.
And so that's the experiment. And you say, well, what if you connect it to ground? Put a meter here. Here's the Earth. Well, so what? I don't see how it makes any difference. You want to put a meter here? That doesn't change the potential from here to there. Potential is a difference between one place and another. You want to raise the whole thing up to 1,000,000 volts from ground? That doesn't matter. People do experiments like that all the time. It's still the same potential here. So that I'm throwing out. Then there's the thing about I thought that idea was really pretty interesting. You spin the magnet, and you wonder, well, does, let me get this light.
It's all right. We can more or less see it.
All right. So you spin the magnet. You wonder, well, does the disk spin? Well, if there's any asymmetry in the field, then you will get you'll induce voltages or whatever in the disk. If it's perfectly, I would say put a coil here to test to see if the field changes, and then see if it spins the disk around. Okay. So if there's any asymmetry and any wobble at all, you'll make the disk spin. So to just say, well, it spins, it's not enough information for me to just listen to it at all. You have to do a control test of some kind to see, well, does a uniform magnetic field induce anything to make a mechanical motion in the disk? Well, that's easy to test. You put some control on it to see, well, does it induce into a coil? You just put a test coil here somewhere. So those are my few comments.
Yeah. You've mentioned about 3 points there, which Jim might like to come back to.
Yeah,
briefly.
all right.
Could I just briefly address your first point quickly? It seems to me that if you're using things like the Lorentz force, well, then you're countering Jim's thesis, and you're saying that this thing is basically electromagnetic rather than electrostatic. Now, some of the points made earlier, made maybe by Harry, certainly made by me. I think we agree. I'm not sure, but speak for Harry. But my position was that the Lorentz force was not erroneous. It just wasn't general enough. It could be generalized. So Jim, would you like to address any of the points that Eric has raised just briefly?
Well, I have great respect for the work on that Eric has done about the particle stuff, and I want to write a paper on that, Eric. With regard to the difference between 1 and 2 meters, as I pointed out, with the 2 meters, the difference in voltage recorded would be equivalent to what you get with the single meter. The purpose of having 2 meters is to determine if charge is accumulated in the disk, where you might then have a Coulomb repulsion effect, or is there unipolar induction? And if there's unipolar induction, 1 meter should show a voltage change of the opposite direction of the other meter, indicating movement of charged particles to or from the center and periphery of the disk, as opposed to accumulating charges. And the only way you're going to distinguish accumulation of charges, in other words, an electrostatic generator, is with the 2 meters. So that's why we've got the 2 meters. But of course, we agree that the difference in voltage between the 2 meters would be what you'd get with the 1 meter setup, as Eric pointed out.
Oh, you want to see if the whole disk charges up electrostatically.
Exactly.
All right. Yeah.
And I'm rather amazed, to tell you the truth, that if I've understood the presentations up to this point on this subject, that no one has even considered this. So you can put a little star on my chart for that point if you want to, or not.
Yeah, well, the fascinating thing, and a reason perhaps to put a star on your chart, is not only that the few of us who've spoken recently have not raised this point, but nobody, as far as I can see, has raised it in the last 170 years. And there might be a fundamental reason for that, or it might be sort of something overlooked. I mean, I perhaps was a bit dismissive originally. I just considered it as a hypothesis which would need to be established, and the onus of proof was on the person raising the hypothesis. But you could reasonably ask, why has nobody else homed in on this? And I think we are beholden to Jim for having not only hit upon this idea, but for having done a little work to explain what the process is and how actually we could discriminate between the electromagnetic induction hypothesis and the triboelectric hypothesis in being central to explaining this whole phenomenon of
Well, thank you, Ian, for the kind words, sir. I tried to point out, or I had thought that work after the original work of Faraday in the mid 19th century, the 1830s and 1850s, would raise additional questions. That's why I emphasize that the Van der Graaf generator was apparently invented or published or whatever in 1929, after the work by Faraday in the 19th century. However, when I trying to refresh my memory, because as the years go by, yes, you studied electromagnetics to the hilt over a lifetime, but sometimes, you might want to refresh your memory. So I was surprised to say that this thesis that these effects were not known in Faraday's time was actually wrong, that triboelectricity goes way, way back. I mean, centuries and centuries and centuries of people noticing that objects can get charged with static electricity, and, the amber and so forth, and the rubbing of these stones is very ancient knowledge. And yet nobody has considered the effect, which I guess would be a little bit obscure, that the triboelectric effect can occur between a solid and a liquid, or a solid and gas. Okay. By the way, you could immerse the whole thing in liquid if you want, in water. Put the whole apparatus under water. And everything that I've said should still work the same, because if the magnetic field is polarizing the water molecules, you'd have that triboelectric effect when the disc spins, and bingo, you'd get some voltage. In other words, you'd have a really lousy, cheap-ass electrostatic generator, not thousands of volts, but just a few stinking millivolts.
But one might question as well. I mean, with conventional generators, not where you have the magnet, spinning around its north-south axis, but where we have coils and conventional generators. That's explained quite adequately in terms of electromagnetic induction effects. Now, do you think that, or do you not think that if your hypothesis is to be substantiated, that the triboelectric effect would have some magnitude in those cases as well, and they haven't been measured? We measure everything in terms of electromagnetic induction.
Well, one phenomenon that occurs in science is that people can generate very different models for what is basically fundamentally at the physical level the same phenomena occurring, and they're so that these models are actually redundant representations. And so the general answer to the point that Ian just raised is yes. It could be that the model of unipolar induction and the model of the triboelectric effect are in fact pointing to the same underlying particle phenomena. That's why I went to the binary mechanics lab data, which is at a very fundamental level. And by the way, this data doesn't depend upon any fundamental so-called universal or fundamental constants, which are actually, in fact, unexplained measurements. And that, so if we want to judge the data that I presented from binary mechanics lab, it might be considered to be at a very fundamental level. None of that depends upon any measured constant and its value, measured value.
Yes, because I think you've said on previous occasions, Jim, that these so-called fundamental constants can be derived, from first principles.
Exactly. Yes, that's been done. And in fact, if you take CE for elementary charge and Planck's constant, there are an alpha, the electromagnetic coupling constant. All of these appear in equations where you could solve for one in terms of the other. What does this mean algebraically or mathematically? And it seems that a lot of physicists, if I may say so, I don't want to be offensive, but they seem to be a little bit weak when it comes to math. These equations state that there is redundant information in these fundamental constants. Okay, that these are not independent variables. And furthermore, not only that, it states that they could not be fundamental. I'll repeat, could not be fundamental because they're not independent values. So what I proposed is three constants, which actually are postulated with the quantization of energy, length, and time, which coincidentally, if you look in the constants work, from NIST.com, I believe it is, all of the constants are listed there and the latest values and so forth, that these three values are that I've postulated with the quantization, what I call full quantization, are in fact the units of measurement in physics, and they are independent and invariant.
What did you say those three fundamentals were again?
Well, energy, which we can measure in mass or kilograms. Okay, and with Einstein's equation, it's a measure. You could convert kilograms to joules, for example, or electron volts. So the first is kilograms, and the second is length, and the third is time. So with full quantization of these three units of measurement in physics, the idea is that these are independent values. There is no redundancy. In other words, the kilogram primary, what I call primary constant, as opposed to the secondary constants, like speed of light is the secondary constant. And if my presentation that has been proposed and I think scheduled for a subsequent week is, in fact, showed, I'll be going into this in a lot more detail. But these three, what I call primary constants, are coincidentally the units of measurement in physics and are independent. No one of them depends upon the value of the other. The second, what I call the secondary constants, which everyone else in the world apparently calls the fundamental or universal and immutable constants, all of those secondary constants, like speed of light and so forth, are dependent, have redundant information in them, because they derive from the three primary constants, which are independent. I'd like to see some mathematic inclined people actually prove that the basic equations interrelating the so-called fundamental constants, I'm talking about CH, Planck's constant, etc., can in fact be solved that the primary constants that I proposed are the only possible solutions to those equations.
All right. Well, I'll mention briefly what is in the offing before closing down today. But we're running out of time as usual, and we might have time for one more quick question if anybody would like to post it to Jim. What about the Coriolis effect? Could that induce charge over time?
I'll pass on that because I'm going to have to look up. It sounds familiar, the Coriolis effect, but I just don't remember offhand exactly what it is. I'd have to look that up.
I mean, we're talking about relative motion, and whether it's a sort of a centrifugal type action or whether it's a Coriolis type action might not be very important. That's just my first response anyway to that. Okay, another one just before we finish. If we were measuring for Lorentz induction, would we be able to discern that better by having different sizes of disk? Well, again, it might, but it mightn't discriminate sufficiently between Lorentz and non-Lorentz type induction. But anyway, I'd like to thank Jim very, very much for having gone to the considerable trouble of detailing his ideas, his analysis of this possibility. It's a factor which heretofore has not really been delineated with respect to the question of electromagnetic induction, and in particular unipolar induction, and it is worth looking into further. In fact, it might be worth promulgating this. You may be thinking of this, Jim, in putting these specific questions on paper, maybe publishing them or putting them out in the public domain a bit more than we've done in these meetings. Now, Jim just briefly mentioned.
I could chime in, Ian. I mentioned that on BitChute, I have a channel where there's been a bunch of views of basically this presentation, but just in 26 minutes on unipolar induction problems. And my channel is Binary Mechanics Lab, where the spaces, the two spaces in there, are the underscore characters. So if you want to look up that video to watch a shorter version than what I presented today here, you'll see that, and that's been getting a lot of views. I just put that up a few days ago, and a lot of people have viewed it.
Binary Mechanics Lab. Oh, okay. Well, that's useful for us. But what we're planning in the John Chappell Natural Philosophy Society Saturday chats is next week to have the president, David de Hilster, back, and he'll be engaging in a more general discussion on all these fundamental questions in physics. And then the following week, provisionally, Jim has agreed to come back, actually, because what we've been in correspondence, some of us, with a gentleman by the name of Henri Cornier. I think I mentioned to him, who has some interesting ideas with regard to non-zero photon mass, and explaining a lot of the phenomena that we've been discussing in recent times. And he may be giving us a talk in February, maybe first, second week of February. We're still discussing that with him. But actually, we've been looking at his paper, and we've all been looking at his paper. We've made a few comments and emails, but Jim has given us the privilege of having his analysis put to the question. And in fact, before Henri speaks, he's willing to give a paper on this, and it'll touch on some of the points he's been making just a moment ago about fundamental particles and so on, fundamental quantities. So we're hoping to have that, I think, Jim, provisionally.
I have the slides almost done for that presentation on the Cornier and the Jackson papers.
Well, you're a wizard. I don't know how you get these slides done so quickly and so on. You said to me, if we're going ahead, I'll just get my slides done, and you had them done very quickly.
Well, it's like going back and being a schoolboy again, and you have an assignment.
Okay, you get it done, yeah.
That's what it feels like.
Great. Once again, thank you very much, and thank you very much for helping us out on these talks and giving us a lot of information, a lot of meat for us to digest and talk about further. So we'll be coming back to a lot of these issues at a later stage. So thank you very much. Thank you for all your questions, for all your participation, in particular members of the Green Room, everybody in the Green Room, Franklin, Harry and Eric and Dennis had no hesitation in coming on when we invited them and making some valid points, which I think were of great value for us in further elaborating this whole question, which is a very fundamental question which has been raised by Jim and needs to be addressed in more detail. So I wish you all a very good day. Sorry, Cornelius, we didn't have time to bring you in. I'm sorry about that. We'll have to make up for that because Cornelius always has some interesting points to raise, and we'll have to discuss this more with him. So actually, Cornelius, if you want to catalogue one or two points you were going to raise, and we can come back to them at a later stage, that would be well worth it. But the clock has caught up with us, and I'll bid you all a very good day. It's getting dark here as usual, so I have to prepare for the evening. And I wish you a very good day, and we'll speak again in the not too distant future. So without any further talk, I'll end the presentation now.